Hello students, welcome to series of lectures on digital speech processing. So in this video, you'll be able to learn the topic on the hidden Markov model coin toss example. In the previous video, we have already seen what is the discrete Markov process, what is the property of the discrete Markov process, and we have also seen one example with respect to weather prediction. Okay, now let us look into the coin toss example of the hidden Markov model. Okay, let's get started. So on completion of this lecture, you'll be able to understand the hidden Markov model for the speech recognition. So, this problem is very important to understand how the hidden Markov model we are going to be designing, and the same thing how we are relating this HMM to the speech recognition. Alright, so this introduction part of the discrete Markov process already we have seen in the previous. So first let us look at the functioning of a discrete time, and then we are considering a system that may be described at any time as being in one of the set of n states. So at regularly spaced discrete time, the system undergoes a change of state according to the set of probabilities associated with the state that we are calling as the state transition probabilities. So here we denote the time instances associated with the state changes as t equal to 1, 2 and so on. The actual state at time t is qt. So this is a discrete Markov process. Okay. So what you need to understand, we already seen in the previous video. Once again, recall the same concept here to understand better the next topic. So the probability of qt is a state for a given time t equal to j for a given qt minus 1, qt minus 2 and so on. This can be approximated to only previous state. Okay, probability of qt for a given qt minus 1, where qt is the current state, qt minus 1 is the previous state. So this is the state transition probabilities. So this is the property of the hidden Markov process. So this example also we have already seen. Alright, so this is the weather prediction example. We have taken this as a state diagram. This is the state diagram, and this is the state transition probability matrix. Okay, state transition probability matrix. So this is a problem we have already solved. We have got the answer as 1.536 into 10 to the power of minus 4. Alright, now let us look into coin toss model. So assume that you are in a room with a barrier, that is example a curtain, through which you cannot see what is happening. Okay, imagine a situation, your friend is behind the curtain and your other side of the curtain, and you don't know what is happening at the other side. Okay, now on the other side of the barrier, your friend or a person who is performing a coin tossing experiment using one or more coins. We don't know how many number of coins. Now let us stick to our discussion to only one coin. Okay, so the person will tell you which coin he selects at any time, and he will tell you only the result of each coin flipped. So thus a sequence of hidden coin tossing experiments are performed with the observation sequence consisting of a series of heads, tails like that. So the following sequence can be observed. So as an example, we have got this is a sequence after doing the coin flip performance by your friend. Now, since the number of coins tossed is unknown, we can assume several different scenarios. Okay, so the first scenario is a 1 coin model, second scenario is a 2 coin model, third one 3 coin model, 4, 5 and so on, etc. But what is reasonable model for the 1 coin scenario that we can see in this slide? Okay, so in the 1 coin model, so this is the state 1 as a head, state 2 as a tail. Okay, if the person flip the coin, either probability will be getting the probability of head or the probability of tail. Okay, so this is the observable Markov model. See this sentence in the bracket, this is very important. Observable Markov model. Okay, so observation sequence could be either a head, tail, head, like this is the sequence you'll be getting. Okay, so what is the reasonable model for the 1 coin scenario is that there is no hidden states. Okay, there are no hidden states and there are only 2 unknowns. Okay, there are only 2 unknowns. For that, we can easily calculate what happens to it. Now, next let us look at the model for the 2 coin scenario with 2 biased coins. So in the 2 coin model, this is state 1. For Each and every state you will be getting the probability P1, that is probability of head, and 1 minus P1 is the probability of tail. Okay, and for other state also 2 unknowns. So total how many number of unknowns you will be getting from this coin toss model? 4 unknowns you will be getting. This is the observation sequence. So here the physical mechanism which accounts for how state transitions are selected could itself be a set of independent coin tosses or some other probabilistic events. Okay. Now let us see the 3 coin scenario. So total how many number of unknowns will be expecting? 9. 1, 2, 3, 4. This is 5. This is 6, 7, 8 and 9. Total 9 unknowns for the 3 coins. So see the sentence which is given in the brackets. This is the hidden Markov model. Okay, we do not know how many number of states it is having. Okay, because the friend of yours is performing the coin toss. We don't know how many number of coins he is using. Those are the hidden states. Those states are hidden to us. Okay, so this is the best example for HMM, hidden Markov model. Now, so what is HMM? Suppose that you are locked in a room for several days. This is another kind of an example I am telling. So you try to predict the weather outside. The only piece of evidence you have is the whether the person who comes into the room bringing your daily meal is carrying the umbrella or not. Okay, if the person is carrying the umbrella, you are easily predicting what is the weather outside. That is, it could be rainy mostly. Yes or no? Okay, if the person is not carrying the umbrella, either it could be cloudy or sunny. So this is the way how we are going to be using, because here also the states are hidden. Okay, but the only evidence we will be having is that whether the person is carrying umbrella or not. With that only we will be able to see what is the weather at outside. So assume probabilities as seen in the table. So this is the weather: sunny, rainy, foggy. So these are the probabilities of the umbrellas we will be getting. Okay, so probability of xi for a given qi of carrying an umbrella. So based on the weather qi on some day I. So this is the way how we are going to be calculating. And in the Markov process assumption, we got probability of observation for a given model equal to, it only depends on the previous state. Okay, the current state probability can be depends upon the previous state. That's all. All other probabilities I am not going to be, all other states I am not going to be considering here. A similar example here. But now in this weather example revisited, we are going to be considering the Bayes principle, which is very important for us. Okay, so probability of q1, q2, qn of for a given u1, u2 can be represented as a Bayes rule like this. Probability of u1, u2 for a given q1, q2 into probability of q2 like this by probability of umbrellas. So here u is true for your caretaker. Your caretaker brought an umbrella on a particular day, and which is false if the caretaker didn't brought. So the probability of observation for a given model should be like this. It's the same as the Markov model only. Okay. Now, so this is a problem actually. You need to solve this problem. I am giving this problem to you to solve this. What is the solution for this? So this is the relation of HMM to the speech. Now, so far we have already seen some of examples like weather prediction, and then coin toss model, the person, hidden Markov models, examples, weather example revisited, all the things if you keep aside. Now let us talk about the real things like the speech recognition. So these are the states actually. Now the person is speaking something like that, and that we are going to be having the acoustic waveform. So this acoustic waveform, you are applying window framing and everything. From each and every frame you are calculating the feature vectors. These are nothing but the feature vectors. From the feature vectors we are calculating what is the word that is recognized with already template that is available in the machine, ASR machine. Okay, so this is the visualize how we are going to be looking the same thing, the way how we have already seen the observation sequence. So this is the way. So observation sequence are nothing but the feature vector outputs. So these are the outputs of the feature vectors. Okay, so when you use the MFCC, you will be getting the feature vector from the speech signal. So those are nothing but the observation sequence. Now we are going to be calculating the probability. Thank you, student. Thank you for watching this video.